Hey, Wade Hampton Chem students. Today we're going to be talking about quantum numbers and how they relate to electron configuration. An analogy that you can kind of use to help understand this is the parts of an address. So you can kind of think about quantum numbers as you go from n to l to m sub l to m sub s as being more specific parts of an address. You know, an address, if you want to give the most general piece of information, might say what state you live in. That might be like the N. If you want to get more specific, you could say, hey, I live in this city in this state. I live in Greenville. That might be like your L. If you want to get more specific still, you could say, I want to live in this, or I live on this street in this city in this state. And so that might be like your M sub L. And then if you want to get specific down to a house on a street, then you might be talking about the M sub S. So the idea here is that no two houses have the same address. And just like no two electrons can have the same set of 4 quantum numbers. So if you have all 4 quantum numbers, they are going to give the specific location of an electron in an electron configuration. If we take a look at this in the context of what they really mean, though, in terms of electron configuration, N is the principal quantum number. This is the energy level, okay? So, if we're talking about electrons that are in the 3rd energy level, N is 3. L is the angular momentum quantum number. Now, this is like the type of sublevel. What I mean by that is that the value for L is telling you whether you have an S sublevel, a P sublevel, a D sublevel, or an F sublevel. For our purposes, L is never going to go higher than 3. Okay, 0, 1, 2, or 3. Notice there's a limitation that says N or L can only go up to N minus 1. The reason for this has to do with what kinds of orbitals exist within each energy level. If you take a look at, in the 1st energy level, you have a 1s, and that's it. If you look at an electron configuration in the 2nd energy level, you have a 2s and you have a 2p, okay? In the 3rd energy level, you have a 3s and a 3p and a 3d. As energy levels go up, the number of different kinds of orbitals that you can have increases. Well, let's focus in on, say, the 2nd version here. If n equals 2, then L could be 0, L could be 1, but L can't be 2 because it has to be less than N. And so that rules out the 2D. And this makes sense because if you look at electron configurations, if you've watched my other videos, there's no such thing as a 2D. Okay, so that helps to explain that from a variable standpoint. Now, the magnetic quantum number, this gets specific down to a certain box in an orbital diagram or a certain orbital in a sublevel. What I mean by that is, for example, let's focus in on that 2p again. If I had a 2p orbital and I was looking at an orbital diagram, it's got 3 boxes, okay? If n equals 2, then L could equal 1 in this case because it's a p, and m sub L has 3 possible values then, -1, 0, and 1, because it can go from -L up to L in integers. Those 3 numbers correspond to these 3 different boxes here, okay? If you were to do this with a d orbital, L would be 2, and then you go -2, -1, 0, 1, 2. That's 5 possible numbers, which is why a d sublevel has 5 boxes. Finally, the spin quantum number. This pretty much tells you whether the electron is spinning up or the electron is spinning down. Okay, if you've got a positive 1/2, we might be talking about an up spinning electron, or a negative 1/2 corresponds to a down spinning electron. Okay, let's put this in the context of an electron configuration. All right, so suppose I wanted to use quantum numbers to talk about all of the electrons within a certain energy level. I might be able to say, okay, just n equals 2. All right? Well, that's going to correspond, if I don't give any other information, that's going to correspond to all of the electrons that are in energy level 2. And there's 2 parts of an electron configuration that have energy level 2, the 2s and the 2p. So if I only said energy level 2, there are 8 electrons in an electron configuration that could have that quantum number. I can get more specific if I add other quantum numbers. Okay, so let's look at a different scenario. Suppose I was talking about a scenario where I said, all right, n equals 2 and L equals 1. Now, if you remember, S corresponds to an L that is 0. P is when L is 1. D is 2 and F is 3. So what we're saying here basically is we're talking about 2p. Okay, so we're talking about those electrons in the electron configuration. I've gotten more specific by telling you, hey, we're not talking about the s electrons, we're talking about the p electrons if L was 1. So there's 6 electrons that could possibly have those 2 quantum numbers in the same atom. If I wanted to get more specific still, and I could say, okay, I want to talk about those 2 electrons right there, then I could say, all right, well, n is equal to 2, L is equal to 1, because we're still talking about a 2p, just like we were before, but this time I want to specify that orbital within the 2p sublevel. That's my m sub L quantum number. Now, m sub L ranges from negative L up to L, so here we're talking negative 1 up to positive 1, negative 1, 0, 1. Looks like the middle box is going to be the 0 here, so I could say m sub L equals 0 for those 2 electrons. If I wanted to get more specific still, then I could say, all right, what if we're talking about, switch colors here again. What if we're talking about that electron only? Well, I'd have the same information I had before in terms of n equals 2, because we're in the second energy level, L equals 1, because we're talking about 2p electrons, m sub L is equal to 0, because we're talking about the middle box in the 2p, and m sub S would equal to negative 1/2 to indicate that the electron is spinning down. Basically, m sub S could either be, positive 1/2 for an up-spinning electron or negative 1/2 for a down-spinning electron. Now notice, no other 2 electrons can have these same 4 quantum numbers in this atom because we've specified not only the energy level, the sublevel, the orbital in that sublevel, but that the electron is spinning down. The other electron that's in here can't spin down according to the Pauli exclusion principle. 2 electrons in the same orbital have to spin in opposite directions. So this other electron would be exactly the same, except for m sub S would be positive 1/2. All right, let's try this in a couple of different scenarios here. All right, so here's some scenarios where basically all I've asked you to do is to identify the sublevel that the electrons are going to reside in here. I also said if a set of quantum numbers is impossible, just say that it's impossible, okay? And most of the time that's going to come in the form of, hey, we're talking about an orbital or a sublevel that doesn't actually exist. Remember, S's show up in the first energy level, S and P's show up in the second energy level, S, P's, and D's show up in the third energy level. So in lower energy levels, you may not see some of the shapes that you see in higher energy levels. Well, in the first scenario here, we've got n equals 3 and L equals 2. All right, so if n equals 3, we're talking about the third energy level. And if L equals 2, remember, start at 0 with S, P, D, and F. If L is 2, we're talking about a D sublevel. So we're talking about an electron in a 3D sublevel. Now, I do have more information here. This is going to tell me the box, and this is going to tell me the spin of the electron there. This is a possible value for m sub L because L can go from negative L up to positive L. All right. So, but we just wanted to identify the sublevel here. Now, in the second scenario, n is equal to 1 and L is equal to 1. Well, n equals 1 tells us the principal energy level is just 1. And L equals 1 tells us we're talking about a P sublevel. Well, the problem with that is there's no such thing as a P sublevel. The first P doesn't show up in electron configurations until you get to energy level 2. So this is impossible. Okay. For the third scenario here, we've got a set of quantum numbers that has n equals 4, so we know the principal energy level is 4. L equals 0, which tells us that we're talking about a 4s. Now 4s is a perfectly reasonable sublevel. 4 has S, P, D, and F, so that would work just fine. Also is a good idea to check your M sub L here. Can M sub L be 0 if L is 0? Yeah, that works out. Okay, M sub L goes from negative L up to L. So actually this is the only possible value you could have for M sub L. Negative 0 to positive 0 is just 0. Okay, that's the reason why S only has one box representing one orbital in an orbital diagram. If we wanted to get more specific, we could say, hey, this electron's spinning up in this box. Okay, now looking at this from a different aspect, I want to see if we can see how many electrons in the same atom could have the quantum numbers that are given here. If you're more specific and you have more quantum numbers, that may be less electrons. If you have all 4 quantum numbers, remember that can get you down to 1. If you have a generalized information, then you may be talking about more electrons. Okay, this first scenario, it only gave us one piece of information. It said n equals 3. Well, think about an electron configuration. All right, I'm just going to do a quick one here. At least to get up to energy level 3. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Looks like I've gone past energy level 3 here. And if I only give you energy level 3, the parts of this electron configuration that are in energy level 3 are your S, your P, and your D. We're talking 3s2, a 3p6, and a 3d10 could possibly have the quantum number 3. Now, you'd have to get more specific with other quantum numbers to talk about the other ones there. Well, total, this is 2 plus 6 plus 10. 18 electrons in the same atom could have a quantum number of 3. You'd have to diversify those 18 electrons with other quantum numbers if you wanted to get more specific. For the second scenario here, we're saying n equals 4 and L equals 1. All right, so we're talking about a part of an electron configuration where the energy level is 4. Now, energy level 4 has a 4s, a 4p, and a 4d. The L here, and an F, the L here specifies which sublevel we're talking about here. Remember, start with S at 0 for L, P, D, F. If we're talking L is 1, then what we're talking about here is we're limited to the 4p. So this is just a 4p, which could hold up to 6 electrons. Now, there's 3 boxes, 3 orbitals, each that has a positive and a negative M sub S for those positive and negative 1/2 spins. So that could give you the 6 possibilities that you have there. But ultimately, we're saying no more than 6 electrons in the same atom could have those quantum numbers. Now, if we've got this last scenario here, looks like we got all 4 quantum numbers, and so you may be tempted to say, oh, we got all 4 quantum numbers. Okay, so we got to be talking about 1 electron, because no 2 electrons in the same atom can have the same 4 quantum numbers. And assuming those are valid quantum numbers, you'd be correct. Threw a little monkey wrench in here when I said n is 2 and L equals 2, because this would correspond to a 2. If L is 2, we're talking about a D. And there's no such thing as a 2D. So this is another impossible scenario, which means we're talking about no electrons. No electrons in an atom can have L equals 2. So we don't really even have to look at the other quantum numbers to know that that's not really going to be valid there. Okay? All right, so in summary, as you get more quantum numbers, the number of electrons narrow down. If you have all 4 quantum numbers, you can have a single electron. If this had been a 1 here, and I was talking about a 2p, just for case in point here, I'd be saying this is 2p, this is 1, this is 0, M sub L is -1, 0, and 1 to correspond to those 3 different boxes. And we're talking positive 1/2 means the electron is spinning up. And so if I had that scenario, I may be able to narrow it down to a single electron, assuming you have a valid set of all 4 quantum numbers. Okay? All right, that's all the time we've got for quantum numbers today. See you next time.